What comes to mind when you hear the word X-rays? What about ultraviolet or UV light? You've probably run into both of these terms at some point in your day-to-day life. X-rays may have come up at the hospital or dentist as a tool for making pictures of our bones, or at an airport when your suitcase is being screened by security. Comic book superheroes with X-ray vision do something similar, magically peering through walls and interlocked safes. As for ultraviolet light, a lot of us know it as that pesky thing that gives us sunburn, or as a forensic tool used in TV shows to illuminate evidence at a crime scene. These are familiar types of light, but what exactly do they have to do with astronomy? X-ray and UV light are actually invaluable pieces in the puzzle of observational astronomy. These types of light have shorter wavelengths than the light we can detect with our eyes, and can be emitted by a broad range of objects or energetic phenomena in our universe. Studying the sky in the X-ray and UV can illuminate entirely new areas of physics and answer important questions about how the cosmos works. The catch comes when we consider how we detect these types of light, and where we have to go in order to do it. Let's go back to some of our earlier programs and look once more at the electromagnetic spectrum. Remember, we can sort out light according to its wavelength. We like to put the light that we can detect with our eyes, what we call visible light, right in the middle of the spectrum, with red on the right and blue on the left. But this represents only a tiny fraction of the electromagnetic light. If we move further to the right to longer wavelengths, we quickly reach something called infrared, which is past the limits of our kind of vision, but which other animals like mosquitoes and goldfish can utilize. Cool young stars and even little dust grains drifting through space all emit infrared light. Pushing out to even longer wavelengths, we find ourselves in the microwave, and then into the radio regime. These are very long wavelengths detected by radio telescopes, which we talked about in an earlier program, and can be used to study everything from the moments after the Big Bang to supermassive black holes. But what happens on the other end of the spectrum as we move to shorter wavelengths? To understand what we see and study here, we need to remember the relationship between the wavelength and the energy of light. We looked at this when we talked about the cosmic microwave background. The energy of a photon, E, is equal to h, Planck's constant, times c, the speed of light, over lambda, the photon's wavelength. H and c are both constants, so the equation gives us a clear relationship between the variables of energy and wavelength. If the wavelength of energy gets shorter and the value of lambda goes down, the energy, E, has to increase to keep the equation balanced. This means that longer wavelength infrared and radio light have pretty low energy, and that shorter wavelength light has much higher energy. This is what we see when we move over to the left end of the electromagnetic spectrum. Ultraviolet light is emitted by stars, and we know our Sun emits plenty of it. Very hot and very massive stars actually emit most of their light in the ultraviolet range, making this the perfect wavelength for studying them. We also see lots of ultraviolet light emitted by atoms whose electrons have been excited to higher energy levels. When these atoms calm down and drop back to lower energies, they release that energy as a photon, and watching atoms release ultraviolet light can also tell us a great deal about the composition of distant galaxies and interstellar space. At even higher energies and shorter wavelengths we find X-rays. X-rays come from things like collisions between fast-moving particles which we see around black holes or during supernova deaths of enormous stars, or from superheated interstellar gas that we can see when galaxies collide. At the very highest energies and shortest wavelengths, we even run into what we call gamma rays, which can be produced during the very strange supernova deaths of some massive stars. Looking at the whole electromagnetic spectrum, it's easy to see why we've wanted telescopes that can study the universe in all wavelengths and all energies. We've already talked in past programs about the incredible mirrored telescopes we use to study the lights that we can see, and with a few tweaks those same telescopes can be used to study infrared light. We also explored the unique physics of radio astronomy and how to design antenna and interferometers that peer into this realm of this spectrum. But what about the shorter wavelengths of UV, X-rays and gamma rays? What do we need to study these? We quickly run into two problems. The first is our own atmosphere. We can plot out how much light makes it from space through our atmosphere all the way to the ground as we go, from very long wavelengths to very short wavelengths. If you take a look at these plots, it's not hard to see where we run into trouble, or why we spend so much time studying visible light. The light that we can see with our eyes makes it all the way to the ground without a problem, making this a great place to build our classic mirrored telescopes. It's also pretty easy to study radio wavelengths from the ground. Infrared can get a bit tougher, and astronomers have a few tricks for studying infrared that we'll get into in future programs. But what do we do at the shorter wavelengths? Anyone who's ever gotten a bad sunburn might think that plenty of ultraviolet light makes it through the atmosphere and down to our beaches and backyards, but the truth is that most ultraviolet light cannot penetrate our atmosphere. Instead, it bounces off the oxygen molecules that make up our ozone layer. Similarly, X-rays and gamma rays get scattered by our upper atmosphere, making it very hard to detect any high-energy light from space while staying on the surface of Earth. The second problem concerns the physics of ultraviolet and X-ray light. X-ray light may bounce off the upper layers of the Earth's atmosphere, but we also know that it's capable of penetrating our skin and making pictures of our bones. Reflecting X-ray light with a shiny mirror, like we do with optical astronomy, just won't work. Collecting and studying light at these shorter wavelengths means getting creative with how we design and build telescopes, and how we store the light that they collect. To explore how we solve these problems, let's start by looking at ultraviolet astronomy. On April 21st of 1972, astronomy reached an exciting new milestone. Apollo 16 landed on the moon. Apollo 16 might not sound like an obvious first to you. It was the fifth mission to land on the moon. Astronauts John Young and Charlie Duke were the second crew to drive the lunar rover. Much of their work on the moon focused on exploring the moon's geology and origins, and it built on previous exciting research that had also been carried out by past missions. Still, the Apollo 16 mission did something brand new for astronomy. It operated the first telescope to observe from the surface of the moon. This telescope, specifically designed to observe ultraviolet light, was the brilliant invention of a physicist and engineer named George Carruthers. Just as a footnote, in 2013, the Chinese moonlander Chang'e 3 landed on the moon. As part of its scientific payload, it carried the Lunar-Based Ultraviolet Telescope, or LUT, which was sent to make observations from the moon's surface. As of 2020, it was still sending back data, so there's probably a good chance that it's working till this day. Carruthers had been building telescopes since he was a child. Born in Cincinnati in 1939, by age 10 he had constructed a telescope out of cardboard tubing and lenses bought from a mail-order catalogue using the money he had earned as a delivery boy. At the University of Illinois, he earned a bachelor's degree in aeronautical engineering and then went on to complete an aeronautical and astronautical engineering PhD in just 3 years. Working at the Naval Research Laboratory, Carruthers was soon heading up a project to design an ultraviolet camera and spectrograph that could be taken to the moon. The key challenge that he and his team needed to tackle was designing a detector that specifically responded to ultraviolet light. The technology used for optical astronomy, like light-sensitive glass plates or the imaging tube designed by Kent Ford that was ultimately used to study dark matter, wasn't suitable for the ultraviolet range. First, the telescope needed to filter out non-ultraviolet light, which meant designing new filters that had never been needed on the ground. Second, the ultraviolet photons that made it through those filters needed to react with a light-sensitive material. However, the same chemical compounds that reacted so nicely when exposed to visible light would have a very different response when exposed to higher energy ultraviolet light. Finally, there was a purely practical concern. How would the data be stored? The astronauts certainly wouldn't be carrying cumbersome and sharp-edged glass plates to the moon, but they needed a way to store the images and bring them back to Earth. Carruthers ultimately designed and patented the first ultraviolet camera. The camera passed light through plates made of lithium fluoride or calcium fluoride, compounds chosen because they allowed only very short wavelengths of light to pass through. The light then struck a negatively charged electrode coated with potassium bromide, which would spit out electrons when struck by ultraviolet light. Those electrons were then focused onto a strip of film that would auto-advance after every exposure. Surprisingly similar to classic film cameras some of you may have used for at-home photography. Carruthers' finished telescope, the Far Ultraviolet Camera and Spectrograph, was a small but powerful telescope with a 3-inch mirror. The Apollo 16 crew carried it to the moon and set it up on the lunar soil using a tripod, situating it in the shadow of the lunar lander. Things didn't go quite flawlessly for the little telescope, however. During the mission, John Young and Charlie Duke would occasionally get tangled up in the cables connecting the telescope to its battery, and the battery itself struggled in the extreme temperatures of the lunar surface. The lubricant that was supposed to make the telescope turn smoothly also started to gum up in the cold, leaving the astronauts struggling to wrestle the telescope into place. The telescope did its job, but for all of its efforts the newly invented ultraviolet camera got left behind, exchanged for the weight of moon rocks. Astronauts flew home with just the lightweight canister of exposed film. Still, the film was precious, containing the world's first ultraviolet astronomy images. Carruthers and his colleagues were able to admire the stars and nebulae in our own Milky Way in a never-before-seen wavelength. The telescope's observations also gave us another unique view, pointing back at our own planet to study Earth's atmosphere and magnetic field. In that same image, the ultraviolet glow associated with the aurora could be seen. Carruthers continued his work in ultraviolet astronomy after the Apollo program ended. We may not have sent any more telescopes to the moon until 2013, but we could send more telescopes into space, and a copy of the same camera he created for the Apollo 16 flew on a Skylab mission in 1973. Other ultraviolet astronomy cameras flew on board high-altitude balloons or suborbital rockets, travelling just high enough to leave Earth's light-blocking atmosphere and capture new ultraviolet observations. Ultraviolet astronomy also enjoyed early successes in NASA's fledgling space astronomy program. Nancy Roman, the same scientist who led the start of what would ultimately become the Hubble Space Telescope, oversaw the launch of the orbiting astronomical observatories in the late 60s and early 70s, carrying several ultraviolet detectors and kicking off the era of ultraviolet satellite observations. In 1978, the International Ultraviolet Explorer, or IUE, was launched as a joint collaboration between the United States, the UK and the European Space Agency, and became an early smash success for space astronomy. The IUE ultimately operated for 18 years and became the first space observatory that could be run in real time by astronomers working at operating stations on the ground. Dedicated to ultraviolet astronomy, the IUE revolutionized astronomers' understanding of the hottest and most massive stars, the hot gas churning around supermassive black holes, and even the diffuse dust of interstellar space that cast a shadow in the ultraviolet by blocking this short wavelength light. The IUE observed Venus, Halley's Comet, and even the 1987 supernova that we just learned about in our last program. Today, the Hubble Space Telescope is the most prolific ultraviolet telescope, with 2 different cameras dedicated to capturing ultraviolet light. Many of the famous and beautiful Hubble photographs you have seen include ultraviolet data, corrected to blue or purple wavelengths for the enjoyment of our eyes, but still carrying valuable information that would be invisible without the advantages of being in orbit and the technology of cutting-edge ultraviolet detectors. Hubble is an excellent example of a multi-wavelength telescope, observing ultraviolet, visible and infrared light by combining its classic reflective mirrors with cameras and detectors that have been custom designed for different wavelengths. You might wonder why we don't just keep expanding Hubble's capabilities and add an X-ray camera to the mix. Unfortunately, when it comes to X-rays, it's not quite that simple. As we've seen, X-rays are even more energetic than ultraviolet light, with even smaller wavelengths. This makes them excellent for studying high-energy phenomena in the universe, but it also makes them difficult to capture using traditional telescope setups. Ultraviolet, optical, infrared and radio telescopes all follow the same basic design. Incoming light is reflected off a curved primary dish or mirror. The curvature of that reflective surface, usually a perfect parabola or hyperbola, helps to focus the reflected rays and reproduce an image of the light source. Radio telescopes may look very different from optical telescopes, larger and less shiny to our eyes since they work at longer wavelengths, but the fundamental principle remains the same. Sadly, this principle breaks down when we try to observe X-rays with this same configuration. Shine X-rays directly onto a mirror and they'll pass straight through it. Thanks to their high energies and short wavelengths, it makes capturing images from X-rays incredibly difficult. Still, by the first half of the 20th century, scientists were very interested in the X-ray sky. Astrophysicists of the day may not have known how to capture X-ray images, but they did know how to detect X-rays, using tools like chambers of inert gas that would produce electrons and ions when an X-ray passed through them. The detectors functioned more like light buckets than cameras, simply reporting the presence and the quantity of this sort of light. If you've ever seen a Geiger counter capable of detecting high energy radiation, you're familiar with this sort of detector. Still, they were sensitive enough to discover X-rays from the outer layers of the Sun during a rocket flight in 1948. Even with this early discovery, X-ray astronomy didn't begin in earnest until the early 1960s, thanks in a large part to the efforts of Riccardo Giovanni. Giovanni was born in Genoa, Italy in 1931 and studied at the University of Milan, before coming to the United States as a Fulbright scholar in the 1950s just as the American space program was taking off. Giacconi focused his research on, well, focusing, namely how to design an X-ray telescope that could actually capture focused images of X-rays, rather than simply detecting their presence. Giacconi knew that with the ability to capture X-ray images, astronomy could move from simply collecting high-energy photons to literally seeing the universe in a new light. Admittedly, just collecting these photons was still pretty impressive at the time. While working on an X-ray imaging detector, Giacconi also led a research group that flew Geiger counters atop a suborbital rocket, conducting a brief sweeping search across the sky to search for signs of X-rays from deep space. In June of 1962 they succeeded, detecting an influx of 100 X-ray photons per second coming from somewhere in the constellation Scorpius. The source was eventually named Scorpius X1, the first cosmic ray source ever discovered. By 1970, Giacconi had upgraded from rockets to satellites, leading the launch of Uhura, an astronomy satellite carrying X-ray counters. Named Freedom in the Swahili to recognize its launch site near Mombasa, Kenya, Uhura was capable of detecting X-ray photons, measuring their energies, pinpointing where they were coming from, and studying how the flux of X-rays changed with time. Still, Giacconi's goal of building an imaging X-ray telescope remained. His first idea, first proposed with his colleague Bruno Rossi in 1960, was elegantly simple and based on a design known as a grazing incidence telescope, or Walt telescope. Named after physicist Hans Volt, who first proposed the idea in 1952 while designing an X-ray microscope, a grazing incidence telescope rearranges the traditional light and mirror setup that we've seen in telescopes at longer wavelengths. We know that an X-ray hitting a mirror at a right angle will travel straight through the mirror. However, an X-ray that merely grazes the surface of a mirror will bounce off that surface. It's the photon equivalent of a rock that will plop into a lake when dropped from above, but skip across the surface if thrown at an angle. In other words, if mirrors are positioned so that the X-rays can travel along their surface rather than through their surface, the X-rays will be reflected. Working off Volt's design, Giacconi and Rossi imagined an optical system constructed from a series of parabolic segments, painstakingly curved and positioned such that grazing strikes from X-rays would ultimately end with a focused image. With this design, scientists could capture clear images of the X-ray sky for the first time. The first fully imaged X-ray telescope was launched in 1978, just 10 months after the IUE's ultraviolet telescope. Dubbed the Einstein Observatory, it revolutionized our view of high-energy astronomy in just 3.5 years, studying the energy and shape of supernova remnants like the Crab Nebula, mapping the X-rays emitted from gas churning around enormous clusters of galaxies, and discovering thousands of surprisingly previously undetected X-ray sources across the sky. At the same time that Giacconi was hard at work on orbital X-ray observatories and grazing incident techniques for imaging, another X-ray astronomer, Arthur B.C. Walker Jr., was also making major strides towards capturing X-ray images, working a bit closer to home. Walker was a graduate of the Bronx High School of Science and a first lieutenant in the U.S. Air Force, where he worked on satellites. After leaving the military, he began working at the Space Physics Laboratory of the Aerospace Corporation, eventually directing the space astronomy program and focusing on the same technology that had launched Carruthers and Giacconi's early research literally. Walker was a pioneer of rocket-based astronomy and was particularly interested in studying the Sun. His team launched payloads of more than a dozen telescopes on several suborbital rockets. These flights could only last about 14 minutes from beginning to end, and only 5 of these minutes were spent high enough above the Earth's atmosphere to observe ultraviolet and X-ray light. In spite of this, Walker and his team were able to use these brief flights to capture the first ultraviolet and X-ray observations of the Sun. These wavelengths offer astronomers a unique opportunity to study the Sun's hot outermost layers, known as the solar corona. This is the bright white nimbus of light visible during a total solar eclipse, caused by the solar wind carrying a stream of plasma away from the Sun and into the solar system, and observations of the corona using these short wavelengths helps us to understand the complex physics at play. While Walker was changing the view of our own Sun, Giovanni was continuing to push the limits of X-ray astronomy beyond our solar system. 2 years before the Einstein Observatory was even launched, Giovanni was hard at work on its successor, a larger and even more powerful X-ray observatory. Named for astrophysicist Subramanian Chandrasekhar, a pioneer of theoretical astrophysics, the Chandra X-ray Observatory launched in 1999 and is still operating today. Chandra has captured exquisitely detailed images of supernova remnants, as well as colliding galaxies and enormous black holes. Chandra also studied the surrounding environment of Alpha Centauri, the closest star system to our Sun, to understand how X-ray light might impact the possibility of life flourishing in that system's planets. Giovanni's lifetime of work on X-ray astronomy, from his first rocket observations to his ever-evolving series of orbiting X-ray observatories, earned him the Nobel Prize in Physics in 2002. High-energy astronomy offers us a unique window into the cosmos. The innovations that make ultraviolet and X-ray observations possible have revealed incredible new physics and opened our astronomical eyes to a host of exciting new phenomena. Some of these offer surprises close to home, like Walker's study of the solar corona and Carruthers' observations of our own Earth's magnetic field. Others, like Giovanni's discovery of the first X-ray source outside the solar system, offer puzzles that explore some of the most mysterious and extreme objects in the cosmos. Today, astronomers think that Giovanni's first discovery, Scorpius X1, is a type of system known as an X-ray binary. These binary star systems combine normal stars, stars that might not be entirely unlike our Sun, with some of the most extreme objects in the universe, neutron stars and black holes. We'll be exploring these incredible objects more in our next program. So time has finally caught up with us today. The top of the hourglass is finally empty, and Father Time is tapping his watch, so it's time to make room for somebody else. Until next week, it's bye for now. Everyone stay safe and look after one another. See you later.